Okay, today we will start discussing the gauge problem in quantum mechanics. Perhaps to motivate ourselves towards this very important problem, which is at the heart of all the foundations of all fields of physics, essentially. Not only in high energy physics, it's condensed matter, astroparticle physics, whatever you can think of. Any serious physics has any serious field of physics has this at the foundation. Therefore, it should be understood at this elementary level before moving towards the research. But as I said, to motivate the discussion further, let us start with a very simple and innocent problem. That is the 0 point of the potential energy. You may say, why it is relevant? I will explain why it's relevant. 0 point of the potential energy. Well, you'll see that as the discussion proceeds, this has some kinship, some similarities to the more general, more systematic gauge freedom problem. First of all, to elaborate a little further on this problem, let's look at the classical physics. When I say classical physics, perhaps I should make it classical mechanics. Let's restrict it a little bit. Classical mechanics. Well, classical mechanics, what is the equation of motion? It's Newton's or Lagrange or Hamilton's, but these are all equivalent. So dp dt is the force, the famous Newton's law. Force is a classical concept. And as we have by now learned quite well, in quantum mechanics, it is a potential really which plays a central role. You may say, well, actually in the other versions of the classical mechanics, that's Lagrange's or Hamilton's or Poisson's, it is again the potentials which play a central role. That's true. I don't want to overlook at that fact, but let's focus on this simple Newton's version, because if you would like to really solve these equations and determine the classical trajectories, whether you start with this one or the other ones doesn't matter really. For the conservative systems, this F is given as the minus the gradient of a potential, which is a function of x, obviously, right? Well, because of this very mathematical relation which connects the potential and the so-called, I say so-called force, because force is really very macroscopic and very classical concept. And thanks to quantum mechanics or the other versions of classical physics that we don't really use that anymore. It's not an easy concept really. Anyway, once you have this, the gradient of a potential which is giving you the force, then obviously this is not a unique thing, right? V is not unique. V is defined up to an addition of a constant. V of x, you are free to add this a constant because the gradient of a constant is 0. Both this and this one, which I denote if you want as V prime x, they produce the same force, right? Produce the same force. Which has the meaning that energy, again for these conservative systems, the energy is written as the kinetic energy plus the potential energy. Then if the potential is non-unique up to the addition of a constant, then it brings us to that point. What's the 0 point of the potential energy? It can have any value really. And for classical equations of motions are insensitive to that addition. That's the physics, that's the trajectories, right? they're insensitive. You are free to choose the zero of the potential energy any way you like. Or potential, yes, that's right. Well, how is it in the quantum mechanics? This naive problem, I am still in it. Quantum mechanics. Well, if you're in quantum mechanics, instead of this equation of motion, we have another equation of motion. That's the Schrödinger's equation of motion, who has a formal solution. So I can write either d by dt psi of t is equal to h psi of t, or you can just integrate it formally and look at the time evolution equation. Psi of t is equal to u, or for conservative systems, that is, the Hamiltonian doesn't depend on time explicitly. Well, perhaps to be rigorous, let's write it in this way. That's the integral of that equation. Now, if we are in the Schrödinger picture, in which all the observables are time independent, obviously the most important or central observable is the Hamiltonian, so U is, that particular U which appear in here, is e to the minus I over h bar h t minus t0. Therefore, if you specify a given initial state through a set of course, measurements and everything, you multiply this by that unitary operator, you go to the evolved state. If you want, we can write it, right? Psi t, although it's a waste of time in principle, so it is I over h bar h t minus t0 psi t0. Now the question is the following. Let's do the same. That is, we go from V and add to it an additional piece. Suppose we do the following. We change the V to say V tilde using the book's notation. I define it as the V of x plus an additional V0. You see, I'm addressing the same problem of adding an additional constant part to the potential energy, but of course, as the paradigm is different, in one side there is this equation, which is the second degree differential equation in x is obviously, and here there's another equation in which we are looking at the integrated version of it in the Schrödinger picture. So we have to really ask, how is the evolved state, how the state evolves under this new view obtained from this one. So this leads to what? This leads to, say, h, which is the old h plus v0 if you want. So the new time evolution is carried out by this evolved, well, by this tilde Hamiltonian. What I'm doing in here is that we started with the same initial state, and then in one case we have evolved with the h as it is, using the h, and in the second case we are evolving by an h tilde, which differs from the original h by the addition of this constant piece. So you can split this as e to the minus I over h bar h t0 times e to the minus I over h bar v0 t0. Here it's implicit that v0, this new piece, commutes. It's a constant, it commutes with the constant and homogeneous. It doesn't depend on time, it doesn't depend on space. Therefore, it commutes with the p, that's the kinetic energy. and it commutes with the original part in V. So I could split this. You see, the splitting is a C-number property or a property of the commuting operators. Otherwise, when you have operators, you cannot factorize them in that form, obviously. Anyway, so I qualified why we could do this. Let's move this factor out to the left. T minus T0 times this acting on that gives you what psi of T. So the evolved states under the H tilde and evolved state under the H differs by a phase. So if you are adding the Hamiltonian, a constant piece, if you are adding the potential energy, constant piece, then obviously it means adding a constant piece to the Hamiltonian, but anyway. So what happens is that you have to compensate it by this, as far as the states are concerned, that addition brings an extra phase to the quantum states. So if you are adding some constant piece to the Hamiltonian, you compensate it in the state vectors by multiplying it with the phase. That is going to be a very crucial relationship when we move into gauge problem. Well, of course, it is not only, as far as quantum mechanics is concerned, it is not only true for the time-independent V0. We could have a time-dependent V as the extra piece. That, of course, if the additional piece is time-dependent, piece in potential is time-dependent, you could still use the same argument and you replace this by the following. So again, you need to compensate. Quantum mechanics is more, how do you say, flexible. There is more room for these kind of discussions. If you add an additional piece, you compensate it by multiplying the state vector by the phase. And the phase is given as such, the time integral in this case of the V, additional. That additional piece, so put a V0 there. Well, these things are quite important. The problem is a very naive, as you see, a simple and naive problem. We said 0 point of the potential energy. We know that it doesn't matter in the classical physics and it matters in the quantum physics in the form of an additional phase. Are phases important in quantum physics? Well, in most cases, when you are really dealing with expectation values to compare against the measurements in the laboratory, as the expectation values involves bra and ket, and if you have additional phase in the front and the bra has the opposite one, it cancels. So this presence of this phase doesn't affect the expectation values. But there are some cases, and the book elaborates. I invite you, if you have free time on your own, I'm not going to cover them because we have to move a little fast. There are some physical phenomena in which these phases appear as quantum interference effects. So they are measurable. One is the different version of of the so-called Aharonov-Bohm effect. Well, actually it's known as the Aharonov-Kasher effect, involving the potentials. So it is a physical phenomenon which is detected experimentally. So the presence of this extra phase is not totally irrelevant. There are cases, interference effects, in which you can detect those additional phases brought in due to the shift of the zero of the potential energy. And Aharonov-Bohm is one typical example, although in a different context, in the context of gauge freedom. And there are also a few interesting pages in this book concerning the gravity in quantum mechanics, and how the gravity enters in quantum mechanics, whether you can really detect the presence of gravity via some quantum interference effects. It's a very fundamental problem, because you know that nowadays there is not really a proper quantum theory of gravity constructed yet. And that's one of the most challenging problems in the research area. A proper quantum theory of quantum gravity. Simplest thing is what? I'm not going to write it on the board. This is sort of a cultural side remark. If you look at the gravity problem in the classical mechanics, what is the right-hand side in here? The right-hand side in here is the mg, right? And this one is m d squared x dt squared. And m's cancel. But those of you who are careful, you may say, you make one important assumption in here. You equate the gravitational mass and the inertial mass. Yes, we do. That's the famous equivalence principle which led Einstein eventually to the discovery of the general relativity, right? Equivalence principle. That's true. If you really take the equivalence principle as a series input, then the masses cancel in both sides, and then you get a purely geometric theory of gravitation. It doesn't involve the mass. d squared x dt squared is g. And you integrate this and you find the equation of motion. And that's what led to Galileo to this famous discovery, right? When you drop two balls, one is iron, the other is a baseball, for instance, whose density is of the same size, whose density of very small. You drop them and they hit the ground in the same time, right? Iron and tennis ball, or even something lighter, ping pong ball, same size. Mass doesn't enter, so it's purely geometrical, it's natural. And that's the great discovery of Aristotle. Well, no, falsification of Aristotle's prediction, that's Galileo, right, which opened the way to the modern physics. But when you enter in the quantum mechanics, without going into too much of the detail, what is the potential? The potential is here, mgz, if you take the z as the direction, right? You know that, mgh. You drop the ball from the ceiling, and it has potential energy up there as mgh, hits the bottom with the kinetic energy 1/2 mv squared, and then you again have m eliminated, etc. But the point is that the potential energy is mgz. So when you have the kinetic energy, minus h bar squared over 2m, the del squared, plus mgz. And in the right-hand side, you have the energy. And you cannot really eliminate the m. The m appears in the form of h bar over m. So if you are going to really look for the gravitational effects in the context of quantum theory, you'll see it really, h bar over m. M is not canceling or factoring out. So it's a beautiful field in its own right. And if you want to have some amusement on your own, it's really be beautifully discussed. It's a 3 pages essay, really. It is a little outside of the content that I am planning to discuss in this course, but I thought I should attract your attention to it, so you should really read it. Because I want to turn my attention quickly to the gauge problem proper. And let's skip that and move to the gauge problem in quantum mechanics. The lesson learned from this simple 0 point of the potential energy thing, let me repeat, is that if you add a constant piece or time-dependent piece to the potential energy, shift the origin of the potential energy, and that quantum mechanics is sensitive to it because you pick an extra phase multiplying the state. That is the lesson which we carry over to the new problem, that's gauge problem in quantum mechanics. Okay. What is the gauge problem in the first place? Well, gauge problem comes in when charged particles are in an external classical electromagnetic field. So let me summarize the setting. charged particles in external, I will qualify the word external electromagnetic field. It is the limitation we have in the context of quantum mechanics. If you would like to treat the problem more rigorously and properly, to remove that quotes and saying that we have external electromagnetic field, then you have to go to quantum electrodynamics. That's quantum field theory. The reason why I call it external, because we will treat this classically. It's not quantized. That's classical. Electromagnetic field in which we put the particle in is not quantized. It's treated classically in the context of Maxwell's theory, and the particle we have, the electron or proton, whatever you are putting in that field, is treated quantum mechanically. So when you see this terminology, external, it means it's a classical field. So I could have used charged particle in a classical electromagnetic field if you want. And that's the quantum mechanics of this problem we will discuss. So again, let me repeat that equation. d by dt mv is the F Lorentz, which is Q E plus 1 over C V cross P is the force. Again, this is the Newton's law, right? The rate of change of the momentum is equal to the external force. External force is the cause of the motion of this charged particle in this electromagnetic field. That much you know, right? It's the Lorentz force. If there's no magnetic field, it is the more recognizable charge times the electric field, or etc. But the presence of magnetic field is quite interesting, important in here, because it brings the velocity dependence of the force or the potential into the surface, velocity dependence. So it is a new class and beautiful class of physics, really, the electromagnetism and the interaction, etc. The lesson that we have to extract from here, classically, these quantities are the physical things, electric and magnetic field, right? Whereas in the quantum mechanics, we have been starting with the Hamiltonian, and Hamiltonian has the potentials in it, the vector potential and the classical potential. And that's an important difference, really. E, electric and magnetic fields in one side in the classical case, and vector and scalar potentials are on the other side for the quantum mechanical things. And these two things are not totally independent, right? You know that if you go to proper classical limit, the quantum mechanical equations are supposed to be reducing to the classical equations of motions. And we are going to sort of quickly demonstrate that that really is the case. But E and B are the physical things in the classical context. Physical objects, yes, let's call it. And these are the things which are measured and between the plates of a parallel plate condenser or a magnetic between the poles, south and north poles of a magnet, etc. Question, how are the electric and magnetic fields related to the potentials which enter into Hamiltonian? But it's classical Hamiltonian, quantum Hamiltonian doesn't matter, because we are going to keep the E and B classical, but they will be, of course, function of x, which is to be treated quantum mechanically. We have to be careful about that subtlety. How they are related? Well, the relationship is between A phi family and the EB family is this. There is the A and phi on this side, A and phi, describing the field, and there is the A and B in this side, again describing the same physical field, right? Electromagnetic field. You have two different objects to describe a physical entity, which is the electromagnetic field filling in this space. There are so many interesting things in this relationship. First of all, notice that there is a mismatch even in the number of mathematical degrees of freedom. In the left-hand side, when you have two vector fields E and B, each of them have 3 components, so the number of degrees of freedom are 6, E and B, as far as you count the components. In the right-hand side, in the potential language, you have 4. There are so much, how do you say, secrets, beautiful secrets, really, in these 2 different representations. And that's really the opening up a new horizon in front of us. Well, let's not get into that, because eventually the gauge fixing, etc., are based on this. But I will talk about them only if time permits. Otherwise, I will go rather quickly. But there is something in this set of relations which is worth paying attention to. For instance, if you change A to A prime, which is equal to the old A plus 1 over C df dt of involving an arbitrary function of space and time, I call it F, and and the phi is replaced by the old phi plus 1 over C df dt, again the same function of x and t. The claim that if they produce if they give you E and B, this pair give you E and B, and this pair gives you the same E and B, not anything else. What is the meaning? What do we get out of this statement? Of course, we'll quickly demonstrate that. But what we get out of this is that potentials are not unique. There is a non-uniqueness, intrinsic non-uniqueness. Actually, there are infinitely many A and phi which all yield the same E and B. E and B are the ones you measure in the laboratory. In that sense, they are the physical things, in that sense. A and phi are mathematical, but I'll demonstrate before finishing today that there is a beautiful phenomenon called R.I.P, which these also have physical effects. They are measurable. They are not just mathematical entities, they are physical things in a more subtle manner. Let's demonstrate this first, that indeed the A prime and phi prime family yield the same physical E and B. It's easy, because if you now go to the E prime and write it as the gradient of phi prime minus 1 over C dA prime dt, right? You put the primed potentials to get the primed E. If you substitute in here what? That expression, phi plus 1 over C df dt, to save some time, I'm not putting in the functional dependencies. It's phi plus 1 over C d phi df dt. And here you put the what? You put the A minus df. Then, of course, the first terms, these two, the contributions coming from here gives you E. So there's an E in here, and there are additional pieces. What are the additional pieces? Plus, this term coming from here is minus 1 over C d df dt. That's the first term. And there is a second term, minus and minus, plus 1 over C d by dt df tf. Notice that gradient and d by dt orders are different, otherwise all the same, and the sign is opposite. But we know that space derivatives and time derivatives are totally independent. They commute. Therefore, you change the order of the gradient and the d by dt, and they cancel. Indeed, there is no extra contribution. E prime is E, and you repeat the same analysis for the B. B prime is del cross A prime. You substitute the A primes. The additional piece is del cross del of phi. Okay, curl of the gradient is 0. How do you prove? You go to the index notation. Epsilon ijk, dj and dk, and epsilon ijk is symmetric, anti-symmetric in jk, and dj and dk are symmetric in jk. It's 0. Again, b prime is the same as b. Quickly. You can, please do it on your own. You wouldn't spend more than 2 minutes, I promise. So b prime is similarly, b prime is b. So we have proven this non-uniqueness. There are infinitely many A and phi family which all yield the same E and B. Good. This is called the gauge freedom. And we have to fix, this is called the gauge freedom. And that is not an ambiguity, that's a beautiful, beautiful opening, really. That there is such a freedom, there is such an ambiguity, there are infinitely many A and phi. How do you get rid of these redundancies? Well, you have to go do the gauge fixing. Gauge fixing means you go to a subclass of A phi family and reduce the number of mathematical degrees of freedom. You may say, why? Well, actually, if you have taken optics, you know that light has two polarizations, right? And that's demonstrated in the laboratory by using polarizers. It really has two polarizations, 2 degrees of freedom. And this representation of the electromagnetic field, or Maxwell field to be a little more rigorous, involves 4 potentials, so 4 mathematical degrees of freedom. So it is there are more mathematical degrees of freedom than the physical ones, so you have to reduce the number, and gauge fixing is really doing it. What are the famous gauges? There are several of them, but the most important one is the so-called Coulomb gauge. Probably you have been seeing this in different contexts, and probably you wouldn't make too much out of this. What is Coulomb gauge? Coulomb gauge is imposing a condition, usually, on the A to make it transversal, because if the divergence of it is set equal to 0, the longitudinal component is chopped away, and you have a transverse, the components of it only surviving. But this is one mathematical condition. You have 4 degrees of freedom minus a condition, then it reduces to 3. It's not really fully fixing, fully eliminating the mathematical redundancy, so you have to add to this an extra phi. So usually it's not stated as explicitly as such, but Coulomb gauge is these 2 conditions. If you say, I have an electromagnetic field, which is treated classically, so I call it external, you send some light on an atom to excite this, and you are treating that problem really. And if you say you prepare your initial laser beam to be in the Coulomb gauge, you are ensuring that there is no scalar component associated with that field, and also divergence of the vector potential is set equal to 0. That's called the Coulomb gauge. These 2 conditions, 4 degrees of freedom minus 2 condition, you end up with the 2 physical degrees of freedom, which is equal to the actual number of polarizations, right? Transversal or the longitudinal polarization. 2 physical degrees of freedom and 2 mathematical degrees of freedom. So this eliminates any redundancy in the physics of this. So that is the gauge freedom and gauge fixing in a nutshell, really. Very quick discussion of the gauge problem. Question. Let's go back to the Newton's equation, or its equivalent, whichever is your favorite. But this is the simplest form. This equation is gauge invariant, right? Because it involves E and B. These are gauge invariant things, because if you make a transformation, you get the same E and B. So gauge invariance is sort of built into this equation. Well, there's sort of a slight ambiguity in here. I put the MV explicitly instead of writing the P. You may say, You may start wondering. Well, there is the so-called canonical momentum P and an mv in here. Are they the same? Well, in this context, when you have velocity-dependent potentials, electromagnetism that is, the P, the so-called canonical momentum, and the mv, the so-called kinematic momentum, are not the same. P is the generator of the translations. Remember, in this class, we have constructed the canonical momentum as the generator of the translations. mv, what is mv? How it appears in here? Well, if you really start now with a proper Lagrangian formulation and try to incorporate electromagnetism with this interesting property that is velocity dependent, in the Lagrangian there will be additional term. There will be a q phi, that's easy as far as the scalar part is concerned, and there will be a vector potential part which is minus q over c v dot a. That's really the classical action, right, if you construct it. And then what you get is the following. P is mv is P minus Q over Ca. That is the relationship, really, between the kinematic momentum or kinetic momentum, some people call it both ways, and the canonical momentum. That is the kinetic momentum. And that is the canonical momentum, which is the generator of the translations. That's the reason why when I was writing this equation, so-called Lorentz force equation, I was careful in not putting the P but the MV, because I know that in this case, in the presence of electromagnetism, these two things are not different, the same. Question. If we are in quantum mechanics, we will discuss it in a really proper detail. For example, I will ask the following question. If the classical equation, Newton's equation, is gauge invariant, whatever you do with the A and phi, it is only E and B appearing in the right-hand side, so it's a gauge invariant equation, provided that you are careful in identifying not the P but the MV in here. What about the quantum mechanics? Do we have gauge invariance, or let's be more rigorous, gauge covariance of the quantum mechanical equation? Invariance means the same value, covariance means same form. We know that physics is described by equations, and it's the form of the equations which count, really. Even the principle of relativity, what does it say? The equations of motions are the same in all inertial frames. Whether it's you have the data collected by one observer or data collected by another observer moving with the constant velocity with respect to this one, and they should obey the same physics laws, meaning that the equations have the same form in both reference frames, covariance. That's important in this theory of relativity, and as you move into 508, you will have, in the context of relativistic quantum mechanics, you will see more of it. So here the question, if it is gauge invariant or gauge covariant, whichever language you use, it's invariant in the classical sense. E and B doesn't change. In the quantum mechanics, we have the Schrödinger's equation, right, in one case. Or if you want, you may look at the Heisenberg equations of motions in the Heisenberg picture. But perhaps the Schrödinger's equation is more illuminating in this context, and we will check whether that equation is covariant, whether it has the same form, independent of the gauge choices that you make. You have one set of gauge fields, A and phi, another set of gauge fields, A prime and phi prime. As these are the things which enter into the equation, if I write the equation for the A phi or A prime phi prime set, is the equation, do we have the same equation describing the same physics? It better be, because we know that if you look at the trajectories of a particle in an external field, that is not to be affected by the choice of the gauges. So quantum mechanics, if it should reproduce the classical physics and the classical limit, h bar goes to zero limit, it should be also insensitive to the gauge choice. So it should be gauge covariant, and I will demonstrate the gauge covariance after the break, and we will do more. We will also try to get this equation using Heisenberg picture. So I will discuss electromagnetism both in the context of Heisenberg and Schrödinger picture, and we'll discover all those interesting properties after the break.